Okay, so in this video we are going to shortly analyze one experimental platform that we have developed here in the University of Mondragon for the student, so if they can use it if they want to do any test or whatever it is. So here it is, the power electronic converter. Here you can see one view, and here it is the control that we have, the control hardware that we have developed for controlling whatever it is wanted to control. So by analyzing the power electronic converter, this is a commercial power electronic converter from one manufacturer. This is a two-level converter, and we can reach voltages of more or less 1000 volts at the DC side, and then in terms of current, if I'm not wrong, we can reach 200 amps, root mean square 200 amps. So this is a two-level converter, 3 phases. There you can see the output connectors, and here the cables, so we can connect it to the electrical grid or to a motor or generator or whatever we want to do. Then the semiconductors are here. I don't know if you can watch them, these white elements. There it is one. The second will be not so easy to watch them, maybe better from there. That's the other corner, that will be the third one, and the second one will be in the middle. Maybe from this view here we can watch them. So the semiconductors are touching or are attached to the heatsink. The heatsink is over there, so we can evacuate the heat that produces the power losses due to the conduction and switching losses of the semiconductors. And then there we have the fan. So it creates the wind or the air through the heatsink. That will be connected. I don't know if you can watch. Let me see it. There it is. That's the temperature sensor. So when the temperature goes above one level, the fan will be connected and the heat will be extracted in a proper way. Then, here we can see the bus bar, the two plates, 1 and 2, from below and from above, and connected to the bus bar we can see also the capacitors, maybe from here as well we can watch them, which are these ones, and there is the bus bar. This is the bus bar, plus and negative. Then here we have the manufacturer has put a resistance in order to let's say to discharge the capacitor when there is no voltage. And in this case this element is prepared, so the DC bus is supplied by a DC source. In our case we are using a commercial DC source, such in here, such this one. Then the control hardware that we are using is based on a Texas Instrument microprocessor. So it generates the pulses for the IGBTs, and here we need to implement all the control loops, the current loops of our algorithm. So in this case we are only using one of these converter, but this control hardware is prepared for two. Here it is, the other one that is not connected at this moment. So mainly here is adapting the voltages of the pulses for the IGBTs, for the driver of the semiconductors, which are these ones. This is for one, this is for the second, and this is for the third. Just remember where the IGBTs are, a little bit hidden, and these are the driver. So all these circuits adapt the voltage levels from this microprocessor, Texas Instrument microprocessor, to the driver. Then all these circuits is mainly to adapt the current and voltage measurements that are provided by the power electronic converter. In this case, there we can see, if I can do it, there are three current sensors, those blue ones from the output, taken from the output, AC output of the power electronic converter. So there are three of them, three current measurements that are coming through these cables to these circuits, and they have to be adapted and so on, and they are connected to the microprocessor. So it makes all the control loops. This is one version of microprocessor that we are using. The next generation one, maybe more professional, is this one. Here it is, the microprocessor. Many chips are not mounted yet, but this is the second version that we are developing now. Okay, so that was all.